From the videos on flip-flops, this will bring us into the final topic that we cover in this course, which will be the finite state machines. So we just want to recall the clocked truth tables for the JK flip-flops and D flip-flops given in these two truth tables here. And we're always going to assume that the JK flip-flop is falling edge and the D flip-flop is rising edge, just in all of the examples that we do. So what do we do with this? The age-old question, why is this useful? Well, let's consider the circuit here where we have an exclusive OR gate, we have a JK flip-flop, and we have some clocked input. So this is where we start combining everything that we've learned so far. So we can say that Z is equal to X, exclusively ORed, with Q. And this seems okay on the surface, but now we're going to deal with X being a function of time, and we know that Q is going to be a function of time as well. So what we're going to do is assume that Q is initially in some zero state, as we've been doing by default. And this is where we get into this kind of cyclic nature of filling out the time diagram. So we know that the output Z is tied to the inputs J and K, and those inputs are tied together. So we can also say that J is equal to K, which is also equal to Z. Now, initially, we have no clock pulse, so we know that Q is going to remain 0, but we have X going high. Now, this exclusive OR gate doesn't care about the timing. It doesn't have a clock in it. So when X goes high, because Q is 0, Z will also go high with our exclusive OR. So now, at the first falling edge, what's going on? Well, J and K are equal to 1. We know if those are equal to 1, Q is going to flip values. So during this small amount of time, after this first clock pulse, we would have X being equal to 1 and Q being equal to 1. So in this case, Z would go to 0. Just for some very small amount of time, because X then shoots to 0. And X shooting to 0 and Q being high presents a 0, 1 to this exclusive OR, so Z would go right back to 1. And it would hold that value until the falling edge of the second clock pulse. Where now again, J and K are both equal to 1, so Q is going to flip. Now, when Q flips, we're going to have a 0, 0 condition at this exclusive OR gate, which means the output Z is going to also flip to 0. And then during this interval, before the next clock pulse, X and Q are both equal to 0. So at this final falling edge, we have J and K are both equal to 0, so we don't have a state change. So Q will finish the time diagram in a 0 state, and so will the output because X remains low. So we're left with something that looks like this, which seemed to be a little bit more tedious, and it was. And this is going to branch us into our final topic, which is the finite state machine or state diagrams. So what we want to do is consider the following circuit, where we have two JK flip-flops and an exclusive OR. And the output of the exclusive OR can simply be given by Q1, exclusively ORed with Q2, exclusively ORed with the input X. So what we want to do is just take all of the inputs for Z, which is Q1, Q2, and X. And those are going to be the inputs in our truth table. So we're going to have all of the 8 combinations possible, and we know how to fill out the exclusive OR gate. So that being said, we can start to look at each input, J1 and K1. We have J2 and K2. Notice the inverter here. So what can we say about J1 and K1? Well, they're tied together, and they're also tied up here, which traces back to Q2. So J1 and K1 will be equal to Q2. So we can just make a substitution right there and just keep a note of that. Now, if we look at J2 and K2, you can see that they are the opposite. They are both originally tied to X. So J2 is going to be equal to X and K2 is going to be equal to X bar. So to fill in the values of J1 and K1, along with J2 and K2, we simply look at Q2, and X. So for the first value, we can see that Q2 is equal to 0. So J1 will be equal to 0, and J2 will be equal to 0. You can see that X is equal to 0, so J2 will be equal to 0, and K2 will be equal to 1, because it is the inverse of X. Now we can go through and fill out all these values for J1, K1, J2, and K2. Now from this, we define our new states of Q. So we have Q1 and Q2, and these will follow the truth table of the JK flip-flop. So we know when we have a 0 and a 0 for the inputs, the state won't change. Well, what is the state? It's going to be 0. It's going to be our Q1 value. So our new Q1 value isn't going to change, and that's going to be 0. And we can do a similar process for all of the Q values for Q1, and then the same thing for Q2, where we look at J2 and K2, and then the current state of Q2. So that gets us to fill out our truth table. What do we do with that truth table? Well, this is where we implement the state diagrams. So we're going to do a few things here. The first is we're going to draw a line between Q2 and X. And the second thing we're going to do here is look at Q1 and Q2, and we can see that we have 4 combinations, 0, 0, 0, 1, 1, 0, and 1, 1. So we're going to divide that up. So what we do is graphically express all of these states. So now we can look at what happens. Well, if we're in state 0, 0, Q1 and Q2 equals 0, and X equals 0, the output is going to be a 0. And if we go all the way over here to the right, we can see that the new state is also going to be 0, 0. So what can we say? If we're in state 0, 0, we get back to state 0, 0 by having the input of 0, and we get an output of 0. So we have this 0 being the X, and this 0 being the Z. So let's look at the case when we are in state 0, 0, and we get X equal to 1. Well, from that, we have Z equal to 1, and we go to state 0, 1. So to express that, we draw a line from 0, 0 to 0, 1. Because X was a 1 and Z was a 1, we have 1/1. Now, filling out the rest of this table, you'll see that we have 6 more arrows to draw, and we can do that as follows, where this may seem a little bit chaotic at first, but when you start to realize that this entire state diagram not only represents this truth table, but also can represent this circuit, you can see the beauty in just one graphical expression for everything. And to show another example, we can consider the circuit here, where it's pretty complex. So let's just walk through this. Well, we have an AND gate, and we have 2 exclusive OR gates. And to examine this, we can start by looking at Z, and we can see that we have an AND gate here. So this AND gate is going to consist of Q1, Q2, and X. Now we also have some other gates here. We can call this F1 and this output F2. So we can say that F1 is simply equal to Q2 exclusively ORed with X, and F2 is equal to X exclusively ORed with Q1, and it's exclusively ORed with Q2. And in this example, we're using D flip-flops instead of JK flip-flops. Just take note of that. So we can fill out Z quite simply. And from this, we want to look at the inputs D1 and D2. And what are those? Well, we can see that D1 is tied to F1, and we can see that D2 is equal to F2. So that allows us to fill in those values. And we know that upon the rising edge of the clock, that the new state of the D flip-flop will be equal to what D is. So now what we do is just dissect our truth table, and from this we can start to write out our state diagram. And we know if we're in state 0, 0, and we have X equals 0 as the input, we'll get z equals 0 as the output, and we will stay in state 0, 0. But if we have 0, 0 as an input, x equals 1, z will also be 0, but we'll jump to state 1, 1. And we can fill out the rest of the state diagram in a similar manner. So again, we have this state diagram, and the state diagram entails the complexity of the truth table and the actual logic circuit.